Hello, and welcome to today's webinar on tackling big data with MATLAB. My name is Filion, and I'm an application engineer with the MathWorks. My goal for today is to give you an overview of the different options for working with big data in MATLAB. I am going to assume that you know at least the basics of working in the MATLAB environment, but I'm not going to assume that you already know anything about working with large data sets in MATLAB. By the end of the presentation, you should understand the basics of how to apply these different techniques, and in which situation is each technique appropriate. Now, anytime I'm giving a talk on big data, I think it's always important to start off by defining, well, what do we mean by big data? I think Wikipedia has a pretty good definition. So any collection of data sets so large and complex that it becomes difficult to process using traditional data processing applications. So really, anytime we need to change the way we're approaching our problem simply due to its size, that's when we're running into big data. And this introduces a number of challenges throughout our workflow, whether that's just getting started, so just how do I even approach this problem in the first place? Rapid exploration, so how can I get access to a small part of my problem and quickly prototype on it? How can I take my prototype and write it in such a way that it will scale? And then how can I take that scalable algorithm and run it on the full data set, maybe even out on a cluster? So we'll talk about a couple different techniques today for tackling these different challenges. But I always like to start off with a few best practices for memory usage in MATLAB that I recommend all MATLAB users, regardless of the size of their data, become comfortable with. So number one, use 64-bit MATLAB whenever possible. If you are stuck on 32-bit, you're going to be very limited in terms of the amount of data you can work with at one time. If you're on 64-bit MATLAB, then the limit on the amount of data that MATLAB can handle at one time is really just however much RAM you have on your system. Number two, use the appropriate data storage for your problem. So MATLAB's default variable type is double precision floating point, but if you're only working with something like integers, then use an integer data type and that will take up less memory. Be aware that we have special data containers for things like sparse matrices and categorical data types, which are more memory efficient. And also be aware that some of the more advanced data types like cells, structures, tables, these have additional memory overhead associated with them. Thirdly, try to minimize the number of data copies that you're making throughout your algorithm. So familiarize yourself with MATLAB techniques such as lazy copy, nested functions, in-place operations, and if you're working with object-oriented programming in MATLAB, consider using handle classes. These will all cut down on the number of times you need to make additional copies of your data as you're going through your MATLAB algorithm. So I recommend everyone familiarize themselves with these techniques and use them wherever possible. It can take more medium-sized problems and cut it down so you can comfortably fit it just on your desktop. And even if it won't solve your big data problems, it will at least make them faster and more efficient and easier to deal with. But if we're working with truly massive data, then we're going to need something beyond these pointers here. So we have had a number of techniques available in MATLAB for many years now for working with big data, including things like connecting to databases, doing stream and parallel processing, and working with distributed data, and writing MATLAB algorithms that will run on clusters in the cloud. In the R2014B release, we added some new capabilities for working with big data, including the Hadoop platform, writing MapReduce algorithms inside of MATLAB, and a new data store object. Unfortunately, we do not have time to go through each and every one of these techniques today, so what we're going to focus on is the new data store object, writing parallel for loops, SPMD and distributed arrays, writing MapReduce algorithms in MATLAB, and we'll talk a little bit about connecting MATLAB with the Hadoop platform. As we're going through these different techniques, these are some things to keep in mind as you're considering which approach is going to be appropriate for your particular problem. Number one, the data characteristics for your problem, so what's the size, type, and location of your data. Number two, the compute platform, so are you stuck just on your desktop, or do you also have some cluster resources available? And lastly, can your problem be split up into small portions and analyzed individually, or do you have to operate on the entire data set all at once? So there's three main categories of techniques we're going to talk about today. They lie on this range of increasing complexity of our problem from embarrassingly parallel to what we call non-partitionable, where we simply cannot cut our problem down into smaller parts. There's no way to do that. We just have to work with the entire data set all at once. So the first technique we're going to talk about is over in this embarrassingly parallel situation where maybe we have a massive data set, but we can chop it up into little bits and operate on each bit individually. In that case, we'll simply load one part in at a time, analyze it, and discard it. And there's two main functions we'll talk about for working here. par4 the parallel for loop, and the new data store object. As the complexity of our problem increases, there's two additional techniques we can bring in, either working with distributed memory or writing MapReduce algorithms. We'll get into the details of each of these today. We're going to start in the embarrassingly parallel situation with par4 the parallel for loop. Par4 is a parallel computing construct coming to us from the parallel computing toolbox. We could just work at our MATLAB desktop serially, but if we have parallel computing toolbox, one of the things we can do is open up a pool of MATLAB workers. These workers are really just extra copies of the MATLAB engine. You can think of them as extra MATLAB computational threads. And they can talk with each other, talk with the desktop, and do some computations. So the idea here is if we have a series of independent tasks, and the classic example is a for loop where all the loop iterations are all independent of each other, well, if they're independent, then there's no reason they can't be run simultaneously. So we could take one group of independent tasks, pass them to this worker, another group of independent tasks, pass them to this one, another group to this one, and they can all start processing simultaneously. So let's take a look at a simple example where we have a couple of different image files, and all we want to do is import these and do some processing. So let's hop over to MATLAB. And we've got a simple script here we'll step through for this problem. In this first section, we'll just set up some parameters, and then we'll load in our first example image. So what you see here is an aerial view of some farmland. These darker circles are plots of land that are currently being used for growing crops. The lighter circles are plots that are out of use. So let's say I wanted to look at an entire state, and I wanted to know for each one of these little circle plots, is it in use or not in use? Well, I could try to look at the entire state all at once, but this is a classic embarrassingly parallel problem. There's no reason to look at the entire state all at once. I could break it down into just a series of sub-images that are easier to work with, analyze each one individually, and then just aggregate the results at the end. So that's what we're going to do in this problem. We're going to start off just by running it inside of a simple for loop. So for each for loop iteration, we're going to read in our particular sub-image. We'll do some kind of processing to identify the circles, and if they're bright or dark, we're not going to worry about the details of the image processing here. And then at the end, we can aggregate them together and do really whatever kind of analysis that we want. But the key that we're focusing on here is we're starting with just a regular for loop. And you can see down here that it's printing out which indices is it running through. You can see it runs through 24 of them in about 26 seconds. But in this case, we're in a classic embarrassingly parallel problem. If I analyze one image, that has no effect on how I'm analyzing another image. So if I want to be able to run this in parallel, there's only two things I need to do. Number one is I need to open up a pool of those MATLAB workers. So there's a couple different ways I can do that. Number one is I can just use the parpool command. Notice here I'm telling it to open it up locally on my machine. I have a quad-core machine on my laptop here today, so this is going to open up 4 MATLAB workers on my 4 cores. But if I also have access to a cluster, well, then I simply need to give it the name of the cluster, and I can open up the workers there instead, and my MATLAB code doesn't need to change. It does not care where the workers live. And you see I get a little output here telling me, yes, I am connected. I have 4 of those MATLAB workers running locally on my machine. If I want my for loop to run in parallel using those, well, then I simply need to change for to par4. And now if I rerun this section, now it's going to be running those loop iterations simultaneously. You can see down here it's running through them more quickly. You also notice that it's not running in order. Since the par4 loop is assuming that these loop iterations are independent of each other, it's actually running them in a random order. And you can see this cut the execution time from 26 seconds down to about 10. So if I'm in one of these embarrassingly parallel situations, this is a very easy thing for me to parallelize. All I need to do is open up this pool of workers, either locally or on a cluster, and change for to par4, and I'm going to get the same result. It's just going to run faster. But do keep in mind that this does need to be independent iterations. If I was to introduce a loop dependency here, well, MATLAB will give me a little warning saying that this is going to error because the variable sub-images is indexed in different ways, potentially causing dependencies between the iterations. So that's an important point to keep in mind. So when should we use par4? In terms of the data types, it could be any format of data as long as it can be broken up into pieces, where each piece can then fit into memory. The platform, well, we could work just on our desktop using the parallel computing toolbox to help us speed things up. But if we have access to a cluster, then we can use what's called the MATLAB distributed computing server, install that on the cluster, and that can help us then take those MATLAB workers, and rather than opening them up locally, I can open them up on the cluster, and my MATLAB code doesn't need to change. It doesn't care where the workers live. And as far as the analysis characteristics, this needs to be embarrassingly parallel. All the different parts of your data, these different loop iterations, must be completely independent of each other. So that's our first technique for working with this embarrassingly parallel situation. What about the second one with data store? So data store is a new object in the R2014B release, giving you easy access to data that's too big to load into memory all at once, either a single text file or a collection of text files, either locally or maybe on some network location, or data from a database using Database Toolbox. Allows you to easily do things like preview the data, set the formats, and import just certain parts of it. So let's look at a quick example. This is the Massachusetts vehicle registration data from 2008 to 2011 and has 16 million records with 45 fields per record. And let's say we want to scan through this file and compute the percent of hybrids registered by quarter. So let's hop back over to MATLAB. And again, we've got a simple script we'll step through. So the first thing I need to do is point this data store to where does my data live. In this case, I've got just a single CSV file on my desktop, but this could be a collection of files or a database that I have somewhere. This first CSV file also does not contain the names of the different columns in it, so we've got a little text file here that contains the headers, and we'll also just read that in. So now that I've pointed I know where my data lives, now I can just call my data store, point it to where the data is located, wherever that happens to be, and give it any additional arguments that I want. And if we take a look at what's inside of the data store, you can see it's not the data itself, it's an object that contains information like where is the data stored, information like what's the number of header lines, what's the row delimiter, what do I want to do if I have missing values in my data, what type of format do I want to import the different parts as, just really everything we need to know about how to import this data. So MATLAB will take its best guess as to what these different parameters need to be, but I can also easily set them, for example, if I want to change the variable names. Now, the first thing we typically want to do with our data store is just get a preview of our data. So from wherever my data source lives, MATLAB will read in just the first chunk of it, so I can get a look at, well, did I get the formatting right? Did I get the names right? Does it look like I've got things set up correctly? Now, one of the most common things people want to do with data stores is cut down on the data that we're importing. So I've got 45 columns here, but I probably don't need all 45. So we can very easily tell it, okay, what are the selected variable names that I want? If I set that and then do a new preview of the data, we'll notice that now that's the only part of the data that it's going to even read off of disk in the first place. We can set other parameters, such as selecting the variable formats. Something else that is new in the R2014B release is the ability to read data from disk directly into a categorical data type, rather than needing to read it in as a string and then convert it. This cuts down on the maximum amount of memory that we need to have at any particular point. If we want to work with this data, well, then we need to read the first chunk of it into memory. So we can do this simply with the read command. Notice here in my workspace, it'll give me my new variable test data. It'll tell me it is a table with 20,000 rows and 5 columns. 5 columns, because that's what we selected. Where did the 20,000 rows come from? Well, that's a property of the data store that we can set. 20,000 is the default, but if I know I've got a lot of memory and I can handle a larger chunk at a time, I can set this to be whatever I want. So let's say we want to chunk through this file and perform some kind of analysis on it. Well, first we want to reset our data store back to the beginning, so we'll begin reading from the first part of the file. We'll select the different variable names, so we'll add in all the different quarters. So I know for Q1 2008 through Q4 2011 was each car registered in that quarter. And we'll set our rows per read to be 1 million per read. Then we can start our processing. Now, the idea with the data store is this gives us a convenient way to chunk through large collections of data that don't all fit into disk. So the way we'll typically do this inside of a while loop. So while the data store has more data, so while it has data that we have not yet read in, we will read in a chunk of it. Then we can really do whatever we want with that particular chunk. It is now in memory. In this particular case, we would run that through a for loop. So for each quarter, we'll extract what are the locations for the different cars that were registered. Of those cars, which ones were hybrids. Add up the total number of cars and the total number of hybrids for this particular chunk. And then for each quarter, just aggregate the results for each chunk. So we're reading through one chunk at a time, just accumulating the results. Then we're done. When we're done, we can do whatever kind of post-processing that we want on it. In this case, if we take a look at our current folder, you can see this particular CSV file, not the biggest thing you'll ever see, but it's about 3 gigabytes in size. So this, to me, constitutes a big data problem because I can't just load a 3 gigabyte file into memory on my laptop and do whatever I want with it. But using this data store, I can chunk through it one part at a time. And one of the really nice things about this is if I have some file like this locally on my machine that I want to start prototyping with, well, I can do that here. And then if I get, let's say, a larger collection of files or I want to read in from a database, all I need to do is change where my data store is pointing, and all the rest of my math stays the same. So in this case, it chunked through that 3 gigabyte file. And now that it's done, we can post-process the results, doing whatever we want, like let's say look at how many hybrids were registered per quarter, and maybe do some kind of fit on it so we can maybe make some projections on how is this going to increase in the future. So that's it for data store. It's actually a pretty simple concept, pretty easy to use. So what types of problems should we apply data store to? Well, for the data characteristics, again, it supports reading in from a couple different types. So text data files, so text files or CSVs, reading from databases with the database toolbox, or if we already have data stored on Hadoop, we can actually read it in from HDFS to our desktop if we want to prototype there. For the form of using data store that we just saw, sort of just running inside of a loop and processing locally, this is appropriate only for the desktop. And as far as the analysis characteristics, again, this needs to be able to run in this load, analyze, discard workflow where we're going to operate on one chunk at a time. So as far as the sort of chunking approach goes, well, we just saw data store, but there's a couple of other formats where we have sort of this built-in ability to chunk to make it a bit easier. So for example, if you're working with mat files, we have an actual mat file command that will allow you to load or save to certain chunks of a variable at a time to and from disk. Or if you're working from binary files, we can do the same sort of thing using memory mapping. So we were just talking about the embarrassingly parallel situation, but what if we're not in a situation that's totally embarrassingly parallel? So each chunk is not able to be analyzed completely in a vacuum, but we're not in a totally non-partitionable state where everything has to be in memory all at once. Maybe we can break our problem up into small chunks and then, aggregate the chunks together with some additional processing. Well, this is where a technique called MapReduce can come in. So MapReduce is a very powerful technique that's gotten very popular for analyzing very large data sets. With MATLAB, we can analyze it on the desktop. If we have database toolbox, we could also run MapReduce with data stored in databases. If we have parallel computing toolbox, we can open up additional MATLAB workers to increase our compute capacity and speed up the processing. And if we have data already living on Hadoop, well, we can access it through a data store and develop algorithms on our desktop that run on the data that is stored on Hadoop. We can also write MapReduce and directly run it on Hadoop, either natively using the MATLAB distributed computing server, or we can deploy it with libraries using what's called the MATLAB compiler, and we'll dive into details on that a little later. But let's start with just a conceptual overview of how does the MapReduce programming model work. Well, when we do this in MATLAB, there's three main functions we need to consider. Number one is what's called the MATLAB reducer. Number two is the data store, which we just talked about. And number three is the actual MapReduce algorithm itself. So the MapReducer controls the execution environment. So where is the MapReduce going to run? This could be serially on our desktop. It could be using a local pool of workers to help speed things up. Or we could take the exact same MapReduce algorithm and with no changes, run it on a Hadoop cluster. The inputs and outputs to our MapReduce algorithm are going to be data stores. So the input is a data store object that points to where the input files live. And the output is also going to be a data store object pointing to where the output files live. Lastly, we have the actual MapReduce algorithm. So this takes in three inputs, the input data store and a map function and a reduce function. So I think it's easiest to explain the map and reduce functions with an example. So let's take a look at this same example for the Massachusetts vehicle registration data, but let's take a look at how could we solve this with MapReduce. So let's start in the slides and take a look at just kind of the conceptual approach. So step one is we need to set up our data store. So we point it to where the data lives and pick out our selected columns. So maybe the vehicle type, a couple of the different quarters, and for each vehicle in that quarter, was that a hybrid? We then enter what's called the mapping phase. So in the mapping phase, we read in chunk by chunk from the data store. And for each chunk, we will run it through what's called the mapping function. So the mapping function is something we write, and we can really do whatever we want to the data in the mapping function. In this case, we would apply some operation by what's called the key, which is a grouping variable. So for example, our first key would be Q3 2008. So we take a look at Q3 2008. And let's say in this case, I just want to filter this data. So I just want to be able to save for each car registered in this particular quarter, was it a hybrid or not? So we would see that we have 3 different cars that were registered in that quarter. First one was not a hybrid, the second 2 were. So my mapping function, I would tell it to take this data and save it to an intermediate data store that keeps the results of the mapping phase and holds on to it until the reducing phase is ready for it. So here we're taking this result and we're writing it to disk in a data store. We would then repeat this process for the different keys for Q4 2008 and Q1 2009. Once the mapping function is done with this particular chunk, we would then read in the next chunk and go back through this process, running the chunk through the mapping function, storing these results to the intermediate data store. Once the mapping function has read through all the different chunks in our data store, we then start the reducing phase. In the reducing phase, this will read from the intermediate data store one key at a time. So we'll read in just this first key, and we can then do whatever we want with it inside of our reducing function. In this case, we could simply do a count for how many entries we have. We have 5 cars in that quarter, and then sum up how many of them were hybrids, so 2. So my final answer for each key is going to be the percent of the cars that were hybrids, and in this case, it would be 40%. The reducing phase would then read in all the data for the next key, run it through the same algorithm. So in this case, we would get 4 out of 6, so about 67%. And lastly, we would get 5 out of 7, about 71%. So this is conceptually how we would solve this particular problem with MapReduce. Let's hop back over to MATLAB and take a quick look at some code to be able to solve this. So again, our first step here is to set up our data store. Then we need to look at write our mapper and reducer functions. In this particular case, I'm going to skip over the contents of what's inside the map and reducer functions, since these are specific to this particular problem. And in a minute, I'll point you to a series of examples that will show you how to write mappers and reducers in more general problems. But basically, we set up our mapper and reducer functions. Then we need to set up our map reducer. So we could, by default, just leave it alone, or specifically give it an input of 0, and this will tell it to run locally just in serial on our local machine. Then we take our MapReduce function, give it the data store, and handles to our mapper and reducer functions. And we tell it to run. And now this is going to run just locally in serial mode on my desktop. You see it's here, it's giving me some updates as it's running through my map and reducer, just telling me at what point is it in the algorithm, and it takes about 15 seconds to run. But one of the really nice things about writing this algorithm in this way is if I then want to, let's say, run it in parallel on my local machine, well, all I need to do then is get a handle to the pool of workers that I still have open. So GCP here will give me back a handle to my current pool of workers. Then give that to the MapReducer function instead of a value of 0. And now if I rerun my MapReduce algorithm, now it's actually running in parallel on my local machine. And you'll notice it runs a little bit faster. So that cut it from 15 seconds down to about 8. If I then wanted to take this and scale it to run natively on Hadoop, Well, all we need to do is, rather than getting these workers locally on my machine, I open them up on the Hadoop cluster, take my data store, point it to where the data lives on HDFS, and that's all the changes that I need to make, and my MapReduce code that I write can all stay exactly the same. So if you're interested in learning more about how to write MapReduce functions to solve different types of problems, one good place to start is just in the MATLAB help documentation. So if you just search for MapReduce in the MATLAB help documentation, this is one of the first pages that comes up, and you'll see a series of examples for solving different types of problems using MapReduce, starting with just simple things like how to write MapReduce functions, how to find just a maximum value from a set of data, how to compute histograms, how to do things like covariance or group statistics, or even fit a simple logistic regression model. So we've mentioned Hadoop a couple of times already. If you hadn't heard of Hadoop before, Hadoop has become really sort of the industry standard platform for working with truly massive data sets. If you read into a lot on big data, you may hear of a few other platforms out there or some different processing techniques, but this is really by far the most popular. And there's two main parts to Hadoop. The first is what's called HDFS, which is the Hadoop Distributed File System. So this is Hadoop's way of managing data that's out on the cluster. Has a lot of really nice things built into it, like fault tolerance and data redundancy. So let's say we have a hard drive failure on our cluster. We're not going to lose any data, and our problem's not going to stop. And the reason is that it already has redundant copies of it saved on other places on the server. The second part of Hadoop is the MapReduce framework. Now, Hadoop is an open source Java-based project supported by the Apache Foundation. And for many years, if people wanted to write MapReduce on Hadoop, well, they had to write it in Java, and they had to do it while on the cluster. And obviously, writing in Java on a cluster is not the best way to really prototype ideas. So one of the really nice things about being able to do this in MATLAB is we can start just locally on our machine, writing our mapper and reducer functions. And then when we're ready, we can take them and scale them to Hadoop, this industry standard platform for working with truly big data. All we really need to do is take our data store, point it to where the data lives on HDFS, and our mapper and reducer functions don't need to change at all. And all the extra stuff on how to work with Hadoop all gets taken care of for you. And you really just need to focus on the interesting parts of your problem, these mapper and reducer functions. If we want to be able to connect MATLAB and be able to take our code and run it on Hadoop, well, there's two main ways in which we could interact with Hadoop. Number one is using those MATLAB workers that we talked about, but rather than starting them locally, we start them on the Hadoop nodes. So this requires putting what's called MATLAB Distributed Computing Server out on the Hadoop cluster. This lets us start up those MATLAB workers. Then I write my MATLAB MapReduce code. But instead of starting the workers locally, I start them up on the cluster. Then when I run my MapReduce algorithm, it goes and runs on the Hadoop cluster. So what's actually happening on the Hadoop cluster is it's running a Hadoop Java-based MapReduce algorithm, but inside the Hadoop map and reduce functions, it's actually just calling your MATLAB code and running that against the MATLAB workers that are on the Hadoop nodes. And this is an interactive connection, so we can monitor the progress live and get the results back immediately. But this requires us to have a licensed version of MATLAB on our desktop, and also a licensed copy of the MATLAB Distributed Computing Server installed on our Hadoop cluster. An alternative approach to taking our MATLAB algorithms and running them on Hadoop is to use what we call MATLAB Compiler. So what this does is this takes our MATLAB MapReduce code, compiles it into a standalone component. This component is then licensing and royalty-free. We can do whatever we want with it, use it wherever we like. We could take it and run it just on a desktop. Or we could also take it and run it on Hadoop. However, since it is running our MATLAB code underneath, we do need on the Hadoop cluster to have what's called the MATLAB compiler runtime, but this is just a freely distributable version of the MATLAB engine, so there's no licensing or royalties included with this as well. So both the engine and the component that we use can be used however many times we want in whatever places that we want. And this can then, again, integrate your MATLAB algorithms on your Hadoop cluster, but using this method, the Hadoop cluster does not need any kind of access or connection to any licensed MathWorks product. And we, of course, can pull the results back at the end. So when should we use MapReduce for analyzing our problem? Well, again, the input data needs to fit the formats that our data store can handle. So either textual files and text or CSV files, databases supported by the database toolbox, or data that is stored in the Hadoop distributed file system. And this should be a data set that will not fit into memory. If we have a data set and we can fit it all into memory all at once, then don't even look at MapReduce. There are easier ways to do it, unless we are just at a point where we're prototyping with a small data set and we're eventually going to scale it to not fit into memory. The platforms where we can run this, well, we could run MapReduce just locally on our desktop. So maybe if I had a 10 gigabyte file on my desktop and I wanted some way to chunk through it, I could write MapReduce and just run it on my desktop and not need to worry about a cluster. But I could also take my MapReduce algorithms and very easily scale it to a Hadoop cluster to run on truly massive data. As far as the analysis characteristics of our problems, well, our problem needs to be able to partition into these two different phases. The mapping phase, where typically we're doing some type of filtering or processing the different sub-segments of our data, and then the reducing phase, where we're aggregating these intermediate results and calculating our final answer. So that was MapReduce, and it's useful in many different situations, but something you notice is it does not extend all the way to the right here. MapReduce cannot handle a truly non-partitionable problem. And by non-partitionable, I mean something where we need to work with the entire data set all at once. So the last technique we're going to talk about is what's called distributed memory. So the whole idea with distributed memory is we're going to open up a pool of workers on a cluster. And since these are running on a cluster, they now have access to additional hardware beyond just what we have on our desktop. And that means they have access to additional RAM, additional memory. If they have access to additional memory, well, then one technique we can do is, rather than trying to load our entire data set just into memory on a single version of MATLAB, we can chop it up into chunks and just load one chunk into the RAM for this particular MATLAB worker, one chunk for the RAM on this worker, another chunk on this one. And then there are a series of MATLAB functions from just core MATLAB that are overloaded to automatically be able to deal with this type of distributed data as if it was just a normal variable. The neural network toolbox is also overloaded so that you can train neural networks that on data that has been loaded in this type of distributed fashion on a cluster. We also have lower level control using what's called SPMD, which stands for Single Program Multiple Data. So this is a way in which we could execute MATLAB commands to specifically run certain commands on certain workers with certain parts of data. So let's take a look at a quick example for this, looking at an airline data set. So let's hop back over to MATLAB for our final example today. Here I'm going to shut down my existing profile and just clean everything up real quick. So this airline data file, this is a common example. Some of you may have seen it before. The full data set includes 22 years worth of information. Since I'm just quickly prototyping on my desktop, I'm only going to work with the first two. Since I have two files, I'm actually only going to open up two workers here. But again, if I had access to a cluster and I wanted more workers, well, I could simply specify a higher number of workers, give it the name of my cluster, and then everything else can stay the same. So the first thing I'm going to do here is I'm going to import these different files into the different workers that I have available. So inside of SPMD, I can use certain commands like lab index. This will return which worker is this. So for worker 1, it will return a value of 1. For worker 2, a value of 2, and so on. So here this is going to tell for each worker, which worker are you? Go into the list of files that we have. First worker, grab the first one. Second worker, grab the second one. And then import those files into memory on that worker. Then we'll just check, okay, what's the data type that we get here? And then when we're done, we can do some additional post-processing on this. So there we've loaded it in, and you can see we printed out what's the size and type for this variable t. It's 1 by 2, and it's what we call a composite. And you notice it doesn't take up much memory. Actually, it only takes up a couple hundred bytes. So what's inside of t is just handles to where these different results live on my different MATLAB workers. So I get 1 for each worker. I can then execute additional commands just on this variable t inside of SPMD. So here I can ask, what's the height of t? Store that in just something called len. And so on each worker, it will see for my particular composite array, what's the height of that, and create a new composite array to store the result. And if we then check just what is inside of our composite array here, and just print out the answer, what this will do is it will import the results to just my regular MATLAB workspace and print them out. And we can see that our first data set from 1987 had about 1.3 million entries. From 1988, about 5.2 million entries. And now that this is just in my regular MATLAB workspace, I can do whatever I want with it. Like, let's say, include it as part of a visualization. And so here we're just doing a simple bar chart. 1987, a bit over 1 million entries. In 1988, a bit over 5 million. So using SPMD, we can operate on just different parts of our data that are stored in different workers. We could import the whole thing into our local data set, or we could do something like just sampling on each worker and downloading it. So this will just do a subsample of it, concatenate it into a single table. And so you see here I have just a regular table inside of MATLAB. Has 100 rows from each one of my workers in all the different columns. And I can open this up and look at it like I would any other MATLAB variable. We can continue to do analysis on this. So if I want to clean this data up, in this case, I'll look for all the different canceled flights, diverted flights, and really anything that's missing, and just go ahead and remove those on each individual MATLAB worker. And do some group statistics. So on each worker, I'm going to group my data by airline and year, look at the mean and standard deviation on the departure delay, and then just concatenate the results at the end. And it takes a couple seconds there, just about 2. And then lastly, we could take this, now that we have it back in MATLAB, and just do whatever we want with it. So here for both 1987 and 1988, we're plotting for each airline on the y-axis what was the average departure delay, and then the size of the circle is what's the standard deviation. And from our legend over here, we could click these on and off to see how did these different airlines change between the years. So when should we use this distributed memory? Well, as far as the data characteristics are concerned, this could really be any kind of data, but it must be able to fit in the collective memory across our machines. So this is one of the big differences between the distributed data and working with MapReduce that we saw earlier. MapReduce is an out-of-memory processing technique. It does not need to load the entire data set all at once. That means the size of the problem you solve with MapReduce is not limited by your RAM. But it also means that MapReduce cannot handle a truly non-partitionable data set. With distributed memory, since we are loading the entire thing into memory all at once, we can handle a truly non-partitionable problem, but it must be able to fit in the collective RAM across the portion of the cluster that we have access to. As far as our compute platform is concerned, well, doing this on our desktop, like I was doing right there, doesn't actually help us handle larger pieces of data. But it can be very useful to let us prototype it. So if I'm evaluating these different techniques for handling large data, if I want to look at distributed memory, well, I can actually open up some workers locally, load in a small portion of data, and use all the different techniques and algorithms associated with distributed data just on my desktop, try things out, and then when I get them working right, then I can scale it to a traditional compute cluster or a cloud and work with a much larger piece of data. As far as the analysis characteristics, well, something that makes it really easy is either if everything we need to do has supported functions for distributed arrays. So as I mentioned, there's a subset of the MATLAB language, such as FFTs, IFFTs, eigenvalues, SVD, a lot of the core matrix math operations that are overloaded to automatically be able to do this type of processing. Also, the neural network toolbox is overloaded for it. Or if I want to be able to run algorithms individually on the different parts of data, like we were doing in our example, we could use something like SPMD. So to summarize, what are the different big data approaches we could take on our desktop? Well, again, for starters, make sure you're using 64-bit wherever possible. If you're on 64-bit MATLAB, then really the only limit on how much data you can handle at one time is the amount of RAM that you have on your machine. We have different techniques for being able to access portions of our data at a time, so we could prototype on our desktop. So things like memory mapping of binary files, using data stores to access large text files or collections of text files or even databases. There's also a variety of programming constructs that can help us automate this sort of chunking or streaming processing. One that we didn't have much time to talk about today is what's called system objects. So these are available from different MATLAB toolboxes like DSP, computer vision, communications, and they have the reading, the analysis, and the output already built into to them for this type of streaming chunking processing. We also looked at the MapReduce programming technique, which we could run just on our desktop. We could also use different techniques for increasing our analysis speed, so using the parallel for loops with our multi-core or multi-process machines, or also incorporating GPUs, which is another topic we did not have time to dive into today. But if we have access to a cluster, then we can also scale some of our algorithms to run on a cluster to handle much larger data sets. So if we have just sort of a general compute cluster, well, our parallel for loops for these embarrassingly parallel problems could also be run on a cluster. All we need to do is change where our workers are opening up. Our parallel for loop doesn't care if it's running locally or on the cluster. We don't have to change the code. All we need to do is change where we're opening our MATLAB workers. Same thing is true for SPMD and distributed arrays. If we have access to a Hadoop cluster, we could also take our MapReduce code that we write locally and have it run natively on Hadoop using the Hadoop distributed file system. And again, one of the keys for all of these different approaches is that we could start natively on our desktop, prototype there, and just see, can we do the type of analysis that we need to do with these different techniques? Which one is going to allow me to most easily solve my problem? And then once we've got that figured out, then we can migrate it over to a cluster with no changes to the algorithm on how we're going to solve our problem. So today we went through an overview of the different techniques that are available. Hopefully at this point you have a good understanding of the basics of how to apply them and which situation would each one be most appropriate. If you want to dive into more details on how to apply these problems in different situations, there's a couple of good places to go. For starters, I recommend everyone take a look at 2 different pages in the MATLAB documentation. So strategies for efficient use of memory and resolving out-of-memory errors are the names of those pages. If you just search for those, they should pop up. We also have a page on our website dedicated to all the different techniques for working with big data with MATLAB and some of the different learning resources for them. We also have a page dedicated just to the new MATLAB MapReduce and connecting it with Hadoop. So whether that's running MapReduce locally on the desktop or taking the MapReduce and scaling it to Hadoop, this page contains a lot of additional resources for working with MapReduce. And that's about it for today. Thank you all for tuning in.